In today's lecture, we will explore the fate of stars that start with fairly large masses. If you recall from the HR diagram, those stars that have lower masses, like our own Sun, may end up as white dwarfs after they've gone through the red giant stage and planetary nebula stage. Actually, if they have much smaller mass than our Sun, then they're still burning hydrogen into helium in their core and will do so for a long time. However, if we have a large mass star, it ends up as something other than a white dwarf. We will call that thing neutron stars. Those are stars that start at the upper left corner of the HR diagram on the main sequence. The main tool here in this lecture will be basically it will be very careful observations. On this and the next slide, I will show you evidence for pulsars. It's also a story of Dr. Jocelyn Bell, a North Irish woman that discovered pulsars and at least for a while was not acknowledged in a loud enough voice. Nowadays most people know about her role, and that will be kind of an interesting story in its own sake. Well, talking of evidence, look at the GIF picture on the left. You're seeing a star that turns on and off. Look at it for a while. Now explain it in words. First, and that must be obvious, the star on the left, on the lower right is turning on and off at exact time intervals. Second observation, it doesn't turn on to its peak power each time. This is an example of a pulsar. Within a couple slides I'll show you that it is our best evidence for the existence of neutron stars, and it's the endpoint of most supernova explosions. The Crab Nebula on the right actually contains the object observed on the left. These are radio signals observed with a radio telescope that may look like an array in the bottom and middle, and the bottom middle thing is the array that Jocelyn Bell basically used in order to find the first pulsars, not the Crab Nebula pulsar, but the first pulsars. The picture on the lower left is Jocelyn Bell today. Okay. Her story begins in Cambridge, England, where she was doing her PhD thesis under PhD advisor Anthony Hughes. Her purpose was to get better signal in the sky, observing sources that emit in the radio part of the electromagnetic spectrum. At the time, people were looking for something called quasars. While looking for those, she discovered a highly regular pulse from a different part of the sky. This would be now called Pulsar PS 1919b plus 21 near Vega, not in a Crab pulsar. She recorded something that looked like a signal on the right. It showed the pulse repeated every 1.337302088331 seconds. No, that's not a mistake. The regularity was so unbelievable that Jocelyn and her advisor called it LGM1 for Little Green Men 1. It reminded them of amplitude modulated radio signal, AM signal, as I put on the bottom right. AM signal has the amplitude modulated, unlike FM signal, which has the modulation of the frequency. Of course, soon enough they found out a few more of those LGMs, and they decided that it's not necessarily something like alien information coming, but rather it, according to them, would be a white dwarf star, same as the end of our sun, that was vibrating. Not too long after that, Dr. Thomas Gold from Cornell figured it out. He figured it was a neutron star. Here is the news. The fellow that won the Nobel Prize for this discovery is the advisor of Jocelyn Bell. Not Jocelyn Bell herself, and not Thomas Gold that figured out what it was. Nowadays, Jocelyn Bell is a professor in the Open University of London. She's a Quaker, so maybe she carries no grudge, but everyone else in the astronomical community does. Still, what are those pulsars that Jocelyn Bell discovered? Well, the pulsar Jocelyn Bell discovered had this 1.33 something seconds pulse differential. The Crab pulsar in that supernova remnant has a 0.033 seconds. The shortest one we know of has 0.01 seconds. Well, what's the problem with that? It turns out that in order to emit a strong pulse, the emitting region for this 0.001 seconds has to be 0.01 seconds multiplied by the speed of light. Well, why is that? Let's assume for a second that you have a building that's 300 kilometers by 300 kilometers by 300 kilometers, and you throw on the switch. What's the fastest rate at which the light in every corner of the building will turn on? Whatever it is that changes in the pulsar has to be smaller than 300 kilometers, because that's how far you go in 0.001 seconds, right? Because the signal to the 300 by 300 by 300 building cannot move faster than light. Also, we know that those pulsars have between 1.4 and 1.8 times the mass of the sun, because we found some places where something orbits those things. So if an Earth orbits the sun, and then something like the Earth orbits these pulsars, and they orbit at about the same rate and the same distance, that would tell us what the mass is. Turns out that a guy by the name of Robert Oppenheimer, yes, the head of the Manhattan Project that created the atom bomb, predicted the existence of stars that would be that small as a result of an iron collapse in a supernova. What Thomas Gold of Cornell did is to show that such a neutron star could be spinning fast and shining from the pole, as is in that YouTube video that I put for you, and on the lower right corner. The shining is similar to what happens in the northern region of Earth, the so-called aurora borealis or northern lights. Northern lights on a pulsar actually shine very brightly, and they shine like a light beam that's sweeping outwards, and since it's sweeping outwards and spinning, it's kind of like a lighthouse, shining and spinning, shining and spinning. If it spins so that the beam exactly intersects with you, then you get that pulse we were talking about. Now, how come there is a magnetic field there that creates aurora borealis? After all, aren't neutron stars made of neutrons? If they are, what's creating currents that will create magnetic field? Here's a partial answer. First of all, those stars still have 7% protons and electrons. The full answer is that it's a very tough question, and there is still research going on in that. That field of research is something I actually did in graduate school with my advisor Sashiko Tsurota, and she was an expert in neutron star cooling.